Dr. Shen Li as our speaker. He's from Facebook and he's the research scientist and technical lead of the PyTorch distributed team there. So Shen got his PhD in computer science from UIUC. And after that, he spent some time at IBM and then he joined Facebook. At Facebook, he has been doing great works. For example, his team has done the design and implementation of features in Torch.distributed package that covers many aspects of parallelism. And more recently, with Shen, we have been also collaborating on distributed training of transformer models. That's how we made connections. Today, he's going to tell us, about the new things that are happening in PyTorch distributed. Welcome, Shen. The floor is yours.
Thank you. Thank you very much for the intro, and thank you everyone for joining today's meeting. Yeah, let's get started. This is my agenda today. I'm going to first briefly go over the concepts of PyTorch and PyTorch distributed, and then I will touch more details on distributed data parallel and distributed model parallel using our DDP and RPC, the two main features in distributed package, as examples. And after that, we'll briefly go through some of the hybrid parallel solutions. Okay. So first, what is PyTorch? PyTorch is the open source library that facilitates building deep learning projects. At its core, PyTorch organizes data into n-dimensional arrays, and we call those arrays as tensors. And it also exposes a rich set of operations and transformations on those tensors. And besides that, it also offers the automatic differentiation tool, which we call the autograd engine, which can automatically compute the gradients for you during the backward pass. And what is PyTorch distributed? PyTorch distributed is a set of features that build on top of PyTorch core. And the goal of PyTorch distributed is trying to make training in a distributed system easy. We will see several features in distributed package in this talk. And in distributed training, there are two popular paradigms. The first one is data parallelism, where it wants to solve the problem where the data is too large and we need to have multiple resources to process those data in parallel. In this case, usually there will be multiple models. Sometimes we have one model replica per device, and then those model replicas will be synchronized across different devices. And for the model parallelism, it's trying to solve the problem where the model is too large and it does not fit in one device or one server, so that you will have to partition your model or shard your model into multiple shards and then put a different shard on a different device or a different server, so that you can host a larger models. The PyTorch distributed package offers features for both data parallel and model parallel. And you can also combine these features to build a hybrid parallel applications. This deck here shows a very high level view of the PyTorch distributed package. In the first layer, there are APIs. We have distributed data parallel or DDP, and also the RPC package. And underneath that, we have collective communications and peer-to-peer communications. Peer-to-peer communications, I think it's common, is where you have a caller and a callee, sender and receiver. But for the collective communication, it's this is more popular in the data parallel training. In this case, where you have multiple peers or processes wants to join the same communication operation. For example, say each process has a different number, and then maybe you have 10 processes. And then maybe you want to compute the average across all those different numbers. So to do that, you can use the collective communication, where all the 10 processes are going to join the same collective communication and providing their individual number as the input and getting the average as the output from the collective communication. So those are two different communication patterns we use in a distributed package. And underneath that, you can also choose from different options, communication backend options or third-party options. For collectives, there are Nico. Nico is NVIDIA's collective communication library, or MPI or Glue. And for peer-to-peer communication, you can choose Tensorpipe or process group, or thread. In today's talk, we will mainly focus on the API layer. Basically, I'm going to go through the details of DDP and RPC, and won't touch too much in the communication layer.
Just one question.
Sure.
What is it that in MPI is not supported, but like in a peer-to-peer setting, you would definitely need, so that I know what is the key difference?
Yeah, so MPI actually does support basic peer-to-peer communication. And the reason that we want to build a new Tensorpipe library for the RPC package is because we want to have the communication library understands tensors. We actually will see that later in one slide when we talk about the RPC package.
Got it, thanks.
Sure. Cool, if there's no more question, I'm gonna move on to the first part, which is DDP. So as I mentioned before, DDP is data parallel, where it's trying to address a problem where data is too large and we need to have multiple model replicas. Each device hosts its own model replica. In this example, we have 3 model replicas and 3 devices. And the input is divided into 3 splits so that each model replica can independently process its own input split in the forward pass, and then also call the backward pass to generate the gradients and also update their parameters independently. Then the question for the DDP feature is that how do we synchronize those model replicas in every iteration to make sure that we are actually can converge into the same final model after the training. And before we go to the communication details, I want to first show a code sample. Sorry that in this talk there will be some code samples, but I will make sure that I'll go through every line of the code, line by line. And if I missed anything when explaining code, please feel free to interrupt me at any point. And this one is especially important. I want to make sure all the parts in this code sample is clear, because many of the subsequent concepts are actually built on top of this example. This code sample shows one local training example. And in the first 3 lines, it basically imports PyTorch and some basic concepts from PyTorch. Torch.n is the neural network, which contains building neural network layers. And torch.optim is the optimizer, which contains building optimizers. And then in the next line, the net equals n.linear. We're basically creating a toy model using just one linear layer. And the linear layer contains the weight parameter and a bias parameter. And what the linear layer do is that when you pass the input to the linear layer is going to multiply the input with the weight and then add the bias. And the 10 by 10 here means that we're going to have a 10 by 10 weight matrix. And also means that the linear layers is expecting. I'm sorry, is there a question?
No, I think one of the audience needs to mute.
I see.
Given that you are the host, you can mute audience. I think there is like, very good. Please proceed.
Yeah.
Okay, cool.
And so could you use your mouse so that we know which line you are talking about?
Yeah, I don't know why I don't see my mouse.
Yeah, can you see Shen's mouse? It seems that I cannot see your mouse.
Yeah, maybe I can. In this view, I can see my mouse. I don't know why when I play the slide, I don't see my mouse anymore.
Also use it. Yeah.
Yeah, cool. Yeah, I was talking about this line. We are creating a model using the n.linear, and the linear has a weight parameter and a bias parameter. And what it does is multiply the input with the weight plus the bias. And the 10 by 10 basically means that the weight is the 10 by 10 matrix. And it also means that the linear layer expects 10 input features and an output 10 output features. So this is the toy model we're going to use in this example. And the next layer, we're going to use the SGD as the optimizer. We don't need to understand what does the SGD do. The only thing we need to know for this example is that the optimizer is going to hold on to the parameters in the model. And then later, when the gradients are ready for those parameters, the optimizer is responsible for updating those parameters using the given gradients and also using the algorithm provided by the optimizer. So these 2 lines basically provide the model, prepares the model, and prepares the optimizer. Then the next two lines are preparing some dummy inputs and a dummy label or targets for this training. We're just using some randomly generated tensors with a given size. And then the next line we'll call the forward pass of the model. It passes the input to the net and generate the output. And during this, during the execution of this line, the PyTorch gonna build a autograd graph. So the autograd graph basically records the input and the output of every autograd function. So in this case, as I mentioned before, the linear layer has a weight matrix and a bias matrix. It multiplies the input with weight and the bias. The autograd graph will look like something like, it will record that the output tensor comes from the addition autograd function. And then the addition autograd function has two parameters. One parameter is the bias parameter from the linear layer, and another parameter is the output from the multiplication. And then the multiplication also points to two parameters. One is the input tensor, another is the weight parameter in the linear layer. So after we run this line, we get the output tensor from the model. We also implicitly build a autograd graph, which can be referenced using this output. And then after that, we use the mean square error to compute the loss, to compute the difference between the output we just computed and the target or label to get the loss tensor. And then after that, we call the backward on the loss tensor, which will just traverse the autograd graph, which we have just built during the forward pass to compute gradients for every parameter. And after the backward pass, all the parameters in the model will have a .grad field. And that .grad field stores the gradients just computed in the backward pass. And then when we call optimizer.step, it's gonna reference those parameters and then apply the gradients to those parameters to update the parameter value. So that's a very quick walkthrough of the code sample. I want to pause here a bit to see if there's any question on this code sample.
I assume you're gonna talk about the plot next, like the left lower figure. That's the one that is really exciting.
Yeah. So cool. So if there's no more question on the local training code, let's go back to the original question we had in the slide, which is how to synchronize those model replicas. The local training actually happens independently on each of those model replica and each device. They are going to process their different input splits, so they are going to have different gradients. And the DDP feature is responsible for synchronizing those model replicas. And there are different options to do that. One option is that we can do the synchronization in the backward pass, where whenever a gradient is ready in one process, we kick off a communication, a collective communication, so that we get a global average on that gradient and put that gradient value, the average gradient value, back to the .grad field. And another option is that we can also do the communication in the optimizer step, meaning that we wait for all the gradients are ready, and then we can do the gradient communication or average in one shot, or we can also wait even for the gradients to be applied to the model, and then we do the model averaging in one shot. So those are two options. And when we designed this feature, we actually decided to go with option one, and here's why. So if we look at the figure on the left, the figure on the left shows the latency breakdown of different models on different communication backend. We're experimenting with ResNet 155 and a Roboto model internally. And the backend are Nico and Blue respectively. And the latency breakdown are normalized to 1 because we are more interested in the relative comparison between the optimizer step and backward pass. So from this figure, we can see that the orange part or the red part are the delay of the backward pass, and the gray part are the delay of the optimizer step. So it's clear that the backward pass is way more expensive than the optimizer. And that's why we choose to do the communication in the backward pass, because if we do that with the backward computation, it's likely we're going to have more overlap between communication and computation. So that's why we do that in the backward pass. One thing I want to mention that, so there are also other options than these two options. And beyond that, because the optimizer is actually, you actually can write your own optimizer. So it's possible that there can be a super expensive optimizer that's even more expensive than the backward pass. But in practice, we don't see that often. And for this slide, I just want to mention why we made a decision 2 years ago to overlap the backward pass with the communication. So that's
Shen, I have a quick question for you on that. So when you do this LSS.backward step, what are you communicating across the GPUs? Are you communicating basically the losses, or you're communicating something else at that point?
Yeah, we're communicating the gradients, and the next slide gonna explain that.
Okay, because I thought the gradients are not computed until after you finish the LSS.backward step, right? Isn't that when the gradients are computed, or the gradients are already computed at the beginning of the LSS.backward step?
The gradients are actually computed incrementally. I mean, from the user's API, you actually don't see that, but underneath the, under the hood of a backward pass, the autograd engine actually is working through the autograd graph function by function.
So basically, as I understand it, it'll compute, like say, the last layer's gradients, then the n-1 and the n-2 and n-3, right? And so exactly. As you are computing the n-1 gradient, are you shipping off the nth layer, the previous layer gradients? Is that how you're I'm trying to figure out how the communication overlap occurs with the computation. So like you compute n, you're computing n-1, you ship n. You're computing n-2, you ship n-1. Is that how you're overlapping?
Yeah, that's roughly the idea. But there's a little difference, is that we are not completely respecting the layer boundaries. Instead, we're organizing the layers into buckets. So so that when all the gradients in one bucket is ready, we're going to kick off communication in that bucket and then move on computation to the next bucket. And there are also motivations for this design. So if we look at the first two figures in the first row, it shows how much time it takes to compute the gradients for different number of parameters, where the x-axis is the number of parameters and the y-axis is the time it takes to compute that many, compute gradients for that many parameters when we are using a ResNet 155 model. So from this figure, we can see that the backward pass is actually computing autograd gradients incrementally. It makes sense because if we consider what does the autograd engine do, it traverses the autograd graph. When it meets a autograd function, it's going to compute the gradients for the parameters for that autograd function and the steady dot grad field for those involved parameters, and then move on to the next autograd function. So the gradient computation is incrementally run during the backward pass. And from this figure, it actually means that we actually want to have a smaller bucket size, because if we have a longer bucket size, we will have to wait longer until those gradients become ready before we can kick off the communication. That also leads to a longer lead time. However, if we look at the communication efficiency in the communication backend, the left figure is Glue, the right figure is Nico. We can see that the communication efficiency increases with larger bucket size. These examples are done using different bucket sizes. They are all trying to communicate the same 60 million FP32 parameters. So meaning that they are trying to communicate the same total size of parameters, but using different numbers of buckets, or different size of buckets. And we can see that with Nico backend, as we increase the size of buckets, the total execution time drops. It means that it's more efficient with larger buckets. So these two observations are actually competing with each other. We want to have a short lead time so that we can kick off each communication earlier. We also want to have a larger bucket so that we can have more efficient communication. Empirically, there's no like one solution that fits all the cases. You will have to do some profiling based on what backend you are using, what communication hardware you have, and then set the bucket size for your training. But the high level idea is the same. If we go back to the previous example we saw in the previous slide, we're gonna divide the model into multiple buckets. And during the backward pass, you're gonna first compute the last layer. Say we put the last layer into bucket 1. And then when those gradients are ready, we're going to kick off the all-reduced communication. And then at the same time, the autograd engine can move on to the second bucket. So it means that the second bucket computation and the first bucket communication can overlap. And the same thing also happens to the rest of the communication buckets. So that's
so I have, Shen, I have another question on this. So
sure.
These communication costs with Nickel assume that all the GPUs are on the same server and they're using NV switch, or is this actually using a cross-machine interface, communication interface?
I don't recall for this specific example. I think this example is done on just one machine with 8 GPUs, and they are interconnected with NVLink.
Okay, so this is the question. I guess that's exactly my point is, wouldn't these numbers be substantially different if you have, let's say, instead of having 8 GPUs on the same machine communicating with each other using the NV switch and NV links, if you have 2 machines with 4 GPUs, and if you want to do all reduce on all those 8 GPUs, your communication is now going to traverse the 2 machine links, and that would basically give you a very different optimization point than this particular data, correct?
Yeah, exactly. And also, it also depends on what are the interconnect hardware between those 2 machines, whether it's the InfiniBand or TCP Ethernet. So I mean, we actually don't have a like one solution that works for all the use cases. Usually, we see the application developers trying to profile and try to tune the bucket size and try a few times and get the best answer for their own application.
So does the DDP allow you to automatically decide the size of the buckets, or the programmer or the application developer has to create these buckets when it does this communication?
Oh, DDP automatically does the bucket. So yeah, I should actually show the code of how DDP works. So, maybe we can go back to this slide. So if you want to wrap, say if I want to convert this code into DDP training, the only thing you need to do is something like this.
Yeah.
Yep. And then, sorry.
I guess my question is, does the PyTorch does this for you, or do you have to, does it give you control basically as a user? Can you do this, or you have to rely on the PyTorch to do this automatically?
This can be done in Python, but you will need to use several.
No, not in Python. No, PyTorch. I'm asking you, is it automatic in the PyTorch, or does the user get the control of what the bucket sizes are for their computational fabric?
Yeah, in the DDP constructor, there's an argument called bucket size.
Oh, okay.
I think it's MB, something like that. And then you can set this to whatever value you prefer.
So it's configurable.
It's configurable.
Yep.
Okay.
Shen, I have a question now. So does that mean that the bucket size that you set, so let's say I set a bucket size of, let's say 5, right? So it's always going to take, every subsequent 5 layers and put them in a bucket. Is that right?
Actually, so the actual code is a little bit different than what we're expecting here, I guess. So the 25 megabytes bucket size means that we're trying to pack the gradients into bucket in a greedy manner. So whenever, say, the next, whenever we add one more gradient into the bucket, going to exceed the 25 megabytes limit, we're going to move the next gradient into the next bucket. And so it means that every bucket is actually will be a little bit different depending on the real gradient size. So we're not going to do tensor slicing to always follow the 25 megabytes limit.
Okay. So the next question then is it not possible that I mean, again, like you said, there is no one size fits all solution, but is it not possible that for some use cases that the bucket sizes are actually not like the size of bucket 1 is not the same size as the size of bucket 2. In general, you basically have a list of bucket sizes, if that makes sense. Is it not possible that you have not just one fixed bucket size, but a bunch of different bucket sizes?
Yeah, today it's not possible with the existing DDP API, but we're working on a project called Composable DDP. We're trying to expose as much flexibility to the researchers as we can. So when that's done, you will be able to write your own bucketing function, And in that function, you can decide how to tune the bucket size.
Gotcha. Okay.
I also had some questions, Chen.
Sure.
Maybe I thought the difference between glue and nickel is just the communication aspect, right?
Yes, glue is currently glue is always going to use TCP. So even if you pass a CUDA tensor to glue, you can first move that to CPU buffer and then use TCP to do the communication.
So then how come it affects the red, which is the computation?
Sorry, well, how does it affect the red part?
Yeah, I thought the red part, when you say this red part, isn't it just the computation part?
Yeah, in this figure, yes, this is just the backward computation, and this part is the I mean the rectangles with the slash from top left to bottom right. This part are the communication.
So my question here is, by just changing the communication, how come the red is changing? Is it just because of the normalization effect, because you are normalizing everything to one and it's like a much?
Yeah, we're normalizing everything to one. So
the amount of computation is not changing, just the ratio of it is changing, right?
Yeah, the amount of computation won't change, whereas we're using the same model. So this one and this one should be the same, and this one and this one should be the same.
So Salman, that also explains, because glue is going to be slower in terms of its communication, and as a result, the overall communication time would be more, and it actually spreads the total training time. And as a result, the fraction of the computation actually shrinks over the total computation.
And also maybe more generally, I mean, is it true that when you are training BERT models compared to the, let's say, ResNet, like CNN types, there is more communication needed or not? Like, is there a difference in terms of the amount, or like becomes more communication heavy? If so, are there like quantitative data you can tell us?
Yeah, the communication overhead is proportional to the model size.
Right.
So actually, it depends on which communication hardware you're using. If you're using, say, Ethernet, we will see that the BERT model, the communication overhead will be far more dominant than the ResNet model when you're using a BERT model. But if you're switching to, say, InfiniBand, then the gap will be smaller.
And on the computation side, there is no difference, like the same thing means that if the size of my BERT model is double the CNN model, my computation would also be double? Or is it because since the underlying parts are different, you are seeing something different on the translation?
I cannot say that for sure, because it also depends on the GPU's stream managers. If, say, a GPU has multiple stream managers that can run, say your convolutional layers are kind of small, and that only needs to take one part of the GPU resources, it's possible to have two convolution layers running in parallel. So it really depends on the model and the hardware you're running. Even if we say increase the number of layers in the model by 2x, it's not guaranteed that you will always get a 2x delay in the computation.
Got it. And my last question is, once you do this bucketization, do you see any straggler effect or any synchronization issues, or those things at this scale, they are not important anymore?
Oh, the straggler problem is a very important problem. And actually, we see that problem become even more severe as we are increasing the scale of the training. I mean, using for 32 GPUs compared to using, say, 1024 GPUs, we'll see different effect. When we are using more GPUs, the straggler becomes a more important problem. So I guess that's one of the drawbacks of using synchronized training. Right. And we actually do see that in internal use cases.
So the reason I'm saying that, we do a lot of work actually on various gradient coding methods to avoid the stragglers. Yeah. And that's maybe something that, do you have a quantitative data, like how much is a straggler hurting you in terms of the total runtime? I know it's model dependent, and that's a general question. I want to know, is it like what is the scale of this?
Yeah, I don't have the number on top of my mind right now, but I recall talking to some different teams. If I recall that correctly, it can as large as like 30% or something when in their real training applications. And the reason that even though there is, say, a straggler problem when they're using synchronized training, they still decided to use that. It's because in some production use cases, the model accuracy is super important. They are willing to sacrifice training speed
That's right.
to get the accuracy. So, and yeah, so for asynchronous training, I guess currently the industry does not have a good solution, say, to always guarantee to give the same model accuracy level when switch to asynchronous training. And that's the main reason why, even if they are straggler, they are still trying to use synchronized training.
Very nice. We have done a lot of work there, but I thought a straggler is not an issue. Anyway, we can chat later. Thank you.
Sure. Awesome. Thank you. Thanks for the questions. This is the last slide I have for DDP. So before we move on to RPC, I want to pause here a bit to see if there are any other questions regarding data parallel training.
I have one question. Just I'm not very familiar with the very detail of the training. And in terms of SGD, it is a statistical model. It is possible you don't need to send the gradient of each node, the gradient of all data, but you still send a sample of them because SGD itself is already picking a sample. Or you don't need a or reduce because in either case SGD is already pick up random. Then you can still do communicate, but you don't need to exactly highly synchronize in each step. I'm not sure.
I think that's thanks for the question. I think that's a great question. We actually have a previous discussion with a research team in Ferro Montreal, and what they do is they use gossip communication to update model gradients, and I think that might be due to the same reason you mentioned in the question. So in general, that's definitely possible to just synchronize one part of the gradients in every iteration, and that will save a lot of communication. But again, when we come back to the production use case, I mean, because it cares so much about the model accuracy, and we will need to have some guarantee on the algorithm itself to actually really adopt that in the industrial use cases. But I do see multiple research projects try to avoid using a collective communication to synchronize everything in every iteration, and that do leads to considerable speed up in the total training speed.
Thank you.
Sure. Cool. Then let's move on to the next part, which is distributed model parallel training. As mentioned in the beginning of the talk, the distributed model parallel training tries to address the problem that, sorry, let me enlarge my slides a bit. Try to address the problem that the model is too large, does not fit in one device or one machine, so that we need to partition a sharded model and put a different shard on different device or different machine. And RPC is one solution to achieve that. There are also other solutions. The RPC try to solve that problem by providing three main features. The first one is remote execution, where you can run arbitrary user functions or modules remotely. And this is what you can expect from any RPC system. And the second feature is remote reference. It allows you to access and reference and share a remote data object without actually fetching back the actual data in that object. So you can view this as a distributed share pointer, and it will also do automatic reference counting for you. And the third main feature is a distributed autograd. When we talk about, in the first slide in DDP, we went through the code sample, and I mentioned that there's autograd engine involved in the forward and backward pass. And the problem with autograd engine is that the autograd engine is a per process concept. So when we are trying to go beyond the process boundary or machine boundary, the autograd engine won't scale in that way. If you call the backward on the loss in the last state process, it won't automatically reach out to the other participating processes and compute gradients for you. So the distributed autograd is trying to cover that gap. It has its own ways to stitch together the local autograd graphs and also coordinate multiple local autograd engines to collectively produce the gradients for the parameters during the backward pass. That's the three main features. Let's go into more details into those features. The first feature is the remote execution. Let's first look at the sample code, and then I will explain more details under the hood. The yellow code here are the ones I want to highlight. There are new APIs from the RPC package. The first one is RPC init, and the first argument is the name of the current process. And the rank is the ID, and the word size is the number of processes in this RPC game. This RPC init does two things. The first thing is that it's gonna create a agent running in the background. And when that agent is ready, it can receive and process requests from other peers. So it also means that all RPC processes are peers. We don't have like a server client quality structure. And the second thing the RPC init does is that it also does a rendezvous. So after the RPC init returns, it means that all the peers in this RPC game is ready. You can start sending requests to any peer in this game. There's also an ongoing project that tries to allow dynamic membership in this RPC game. So after that, we should be able to remove the rank and the word size input in the RPC init function. Within the RPC package, there are three ways to do communication. The first one is RPC_sync, and the first argument is the destination, a name of the destination process, and the second argument is the function that you want to run on the destination process. In this case, we're using TorchAdd, which is a built-in function from PyTorch, and then the third argument is the list of argument you want to provide it to the TorchAdd function to run on the remote side. And this RPC_sync function going to block until the response is fetched to the caller. And it also has another similar API, but runs in an asynchronous fashion, which is called RPC async. The only difference is that this API returns a future immediately, and then you can wait on the future to get the result. The third API is a remote function. The remote function also returns immediately. However, the difference between the remote and async is that remote returns a remote reference. And the remote reference, when you call remote, the return value of this function gonna live on the callee of this remote call and will not be fetched back to the caller unless you explicitly call to here on this RF. In contrast, when you call a RPC_async, it is always guaranteed that the return value of my ad will be fetched to the caller in some future time. So that's the main differences. We will see in the next slide why the remote function might be useful. And when we talk about the RPC and communication, one natural question is why do we want to use PyTorch RPC? Can I just use the local PyTorch and connect that with the gRPC and the script to the communication? And the answer is yes, you can do that and it can work. We actually see applications does that. But the nice thing that PyTorch RPC offers is that it understands tensors. So what I mean by understand tensors, if you are trying to build, hook together a PyTorch local training with gRPC or script, those third-party libraries can expect you to pass them maybe a JSON or string or user-defined data type. And then after that, those data needs to be serialized into one message before they are sent out. So if we consider when are we going to use this RPC system, usually it's used during the forward path to send the activation and during the backward path to send the gradients. It means that the argument can be very large activation tensors, can be very large gradients tensors. And so if that's the case, and if we have to serialize and deserialize those large tensors, then the serialization overhead can be a bottleneck in the system. And we actually do see that in some applications. In contrast, PyTorch RPC, when you pass a Python object to the RPC system, the RPC system also going to serialize that object into message. However, you're going to extract out all the tensors and keeping those tensors intact. So the message format of the RPC system is that there will be a vector of tensors. All the tensors are not touched. The storage are kept intact. And then everything else will be packed into a binary payload. By everything else, I mean non-tensor arguments and tensor meta information, function name, etc. And then we pass this message into the underlying third-party communication library. And there was a question why we need Tensorpipe. Can MPI be the backend for RPC system, yes, it can be the backend for RPC system. But the difference between Tensorpipe and MPI is that Tensorpipe will automatically try to pick the best channel for you. Where say, if I have a CPU tensor on the center and then say the sender and the receiver are on the same machine, then it's possible that the Tensorpipe is going to pick the shared memory as a channel to communicate the tensor from the sender to the receiver. And if they're on different servers, they're going to fall back to TCP. And if I have GPU tensors, and say if the two sender and receiver are on the same server, it's likely that Tensorpipe is going to pick NVLink for you. And if they're on different servers, you're going to use InfiniBand if InfiniBand is available to do a GPU RDMA communication. And if InfiniBand is not available, we can go back to TCP. So that's a nice thing of the Tensorpipe backend for RPC communication, which is not available today in MPI. We can potentially build similar thing on top of MPI, but it's just not available yet today. So that's
does the Tensorpipe needs to know the underlying fabric, communication fabric availability, or is it auto-detected also?
It needs to know that. You need to when you set up the when you call the RPC init, there's actually an options argument, and within that options argument, you can specify what are the available hardwares. And the Tensorpipe is actually by picking the best communication media, the Tensorpipe is actually just matching the sender and the receiver's available hardware devices.
And do you do any kind of encryption of the data, or you assume that the peers are all securely connected to each other?
Currently, we don't do encryption. If necessary, it's possible to say build a layer on top of RPC, but we do also got that request from other users. Currently, there's no ongoing projects trying to add an encryption to RPC, but if we see a lot of demand, we'll maybe try to add that into as a building feature.
I see.
I recall there's some MPI RDMA from NVIDIA. They allow you to do GPU to GPU direct communication using enhanced MPI without using CPU. You may, I mean, your RPC may already using this kind of feature, but MPI, maybe underneath the MPI, they also capable of choosing a right channel for you.
Oh yeah, I'm not aware of that. Yeah, maybe MPI has that feature today. Just I'm not aware of that.
Okay.
I think for GPU direct, you need specific interconnects between the GPUs. I don't think as it is, I don't think it works over anything. So I think it's limited in that sense.
Oh,
I see. Cool.
Yeah, but that's not for RPC, right? That's for MPI communication. I mean the GPU to GPU communication.
Right. It's just point to point.
MPI.
Yeah.
Yeah, it's not for RPC.
MPI.
Yeah, I mean, if in the future, say MPI becomes a superset or more efficient than Tensorpipe, it's also possible to have a wrapper to allow to plug an MPI into the RPC system. We have an abstract layer for the communication, and I think it shouldn't be too hard to make that wrapper. So if in the future we see a lot of people requesting MPI, it's possible that we're going to add that into RPC.
So I have a question here. So in your figure, you show the message contains the CPU tensor and GPU tensor. Does this mean that I can construct a message that contains two kinds of tensor, or I can only use one for a single message? Oh,
you can use arbitrary numbers of tensors. Say here I'm just passing in one tensor, right? I can change this to maybe say linear. This is also possible, and then this linear will contain a weight and a bias tensor. What happens in the serialization is that you're going to use the Python pickler, or you can replace that pickler with your own pickler, and then they're going to register a reducer in that pickler, and that reducer is going to specifically extract the tensor. So whenever you see the tensor, you could just extract tensor, that put that tensor into this vector, and then everything else will be packed into the payload. So as long as this argument is pickable from Python's perspective, then it should work.
I see. So it can be a mixture of CPU tensor and GPU tensor.
Yep.
Okay, that's very flexible. Thanks.
Hey, Shen, I will another question. do you observe the situation that data movement between CPU and GPU became a bottleneck instead of just moving data from one server to another? Like, sometimes you have to copy data from one node to another, then you have to copy data from GPU to a CPU memory, then copy data from CPU memory to another node of CPU memory, then move to the GPU.
I see. So in previous work, we do see the application where we have, say, GPU trainers, and then we have CPU parameter servers. And in that case, I recall last time when we work on that, then we are doing GPU to GPU communication, and then on the parameter server side, we are first moving the tensor from GPU to CPU on the trainer, and then do the CPU to CPU communication. But I can't tell whether the CPU to GPU communication become a bottleneck in the system in that work. But there's one recent work, which is the CPU offloading. I think that one actually requires frequent GPU to CPU communication. And in that specific work, the CPU to GPU channel might be the bottleneck for the entire system.
Okay, thank you.
Do you mean the one from DeepSpeed team?
Yeah, I think they are leading that. They are leading that domain.
Yeah, that's a very famous one, using CPU to computing.
Yep. Cool. We have 10 more minutes left. Let me move a little bit faster. The next concept is remote reference. So why do we need a remote reference? Maybe it's will be clear if we walk through this example. During training, it's common that we have maybe one master node or one driver node that drives the entire execution of the training loop. So in this example, I'm going to use the W0 as the driver, and our other peers are the ones that does the real work. And I first define a user function called myAdd. This myAdd just takes the two remote references and fetch the data to itself and then add them together and return the result. And then the following 4 lines are called on W0. First, you're going to call load data A on W1, and then leave the data there, only hold on to the reference of that data. And then you're going to do the similar thing on W2. So after these first two lines, W1 and W2, each of them are holding on to its own data. And the W0 has the reference, a lightweight reference to those data. And then W0 calls another remote to W3, passes these two remote reference to W3, and asks W3 to add those two data together. What happens on W3 is that W3 is gonna reach this function and then call to here on those two remote references. And then this two to here gonna fetch the data directly from W2 to W3 and W1 to W3. And a similar thing also happens from W0 to W4. W0 also tells W4 to fetch the result from W3 and add them together. So after we do this, we can see that the entire orchestrating code are running on W0. However, all the data passes actually does not go through W0. Although W0 are holding remote references to all the data and intermediate results, all the communication passing through W0 are lightweight communications, just the control messages of the remote reference. And all the heavyweight data paths are actually directly going from the data generator to the data processor and etc. So in this way, the remote reference helps two things. One is that the code can stay in one process and it looks easier to understand. And the second, it avoids to carry the data around when you want to move the data from one process to another. I'm going to skip the remote reference counting protocol, but I want to pause here a bit to see if there's any question regarding this example regarding remote reference.
Does this mean that we can develop any kind of training algorithm based on these APIs? Since here you can control any kind of message for different workers.
Yeah, I'm hesitant to make a claim that we can define this can support any training algorithm, but RF itself is pretty flexible. It only sees the data as a Python object. So, and Python object can be anything. So if that can serve the your requirement, then it should work for your application.
Because in your example, you can see the W0 can control all the other workers.
Yep.
Yeah, this is very flexible for, I think it's very flexible for the federated learning, because sometimes we need to design very complex algorithm.
I see.
Yeah.
Cool. Great to hear that. Thanks.
Yeah, very useful API.
Thanks.
So basically, you can define the reference of whatever functions you want, and you can pass them around as a flow to the workers, and you materialize at specific workers that you want. This is the understanding here.
Yeah, exactly.
Yes, it sounds like the W0 is a manager to control the entire network, to ask everyone to do different tasks. Yeah.
So you could define the whole operations that you want to compute as references, and then you materialize them at the specific workers that you need to.
Yes, we actually do see that application internally.
Okay.
Cool. Then the third main feature is distributed autograd. So the question for distributed autograd is how to extend local autograd engine beyond processing machine boundaries. The high-level idea is actually very simple, which is whenever you call a RPC function, we're going to insert a send autograd function on the caller, and then insert a corresponding receive autograd function on the callee. So during the backward pass, say when we call the backward on the callee, and the local autograd engine on the callee will eventually reach the receive function, and the receive function will be responsible for sending the gradient over to its corresponding send function, and then we can proceed the autograd pass in the caller as well. This code on the right side shows a simple example where we first create a context for the autograd. I'll come back to the context later. I'll just explain why we have this context. The first two lines within the context are preparing the parameters. Suppose we have a user-defined function called create requires gradients, basically creates a tensor with requires underscore gradient set to true. And then we also prepare a distributed optimizer. So why do we need a distributed optimizer? Because in distributed model parallel training, your model parameters are scattered across multiple processes. And the optimizer we saw in the data parallel case only works for local parameters. And if we use that for distributed model parallel training, it means that we are forcing users to call those local optimizer on each process. It's going to be a pain. So the solution here is that we provide a thin wrapper distributed optimizer, and which instead of taking the real parameters, you're going to take the remote references of those parameters. And what this class going to do is that you're going to reach out to all the distinct owners of those remote references, and then create a local optimizer on those owners. So in this case, we have Rx on W1, Ry on W2. When we create a distributed optimizer, this thing going to create a SGD on W1 for X and another SGD on W2 for Y. And later when we call step function on this optimizer, it's also going to reach out to all the participating optimizers and to call the step function on those local optimizers accordingly. So that's the distributed optimizer. And then we're going to build some local autograd graph on W1, W2, respectively. Assume that we have user function, just to add a constant to the tensor called myAdd. And then after these two lines, the W1 and W2 will have local autograd graph looks something like this. There's the add function points to parameter X and also a constant 3. On W2, there's the local autograd add function points to Y and a constant 2. And then when we call RE and RB are the result of those two addition functions. And then when we call to here on RE and RB, you're going to incur RPC communication. And then you're going to insert a send on the caller and then a receive on the callee. So after that, these two are going to connect W1, W2 and W0, and also going to connect W1 and W0. And then we can add those two local tensors together to produce summation. And then we sum those tensor into one scalar tensor value to create a loss. So at this line, when the code executes at this line, the distributed autograd graph is going to look like something as the left figure shows. There's a local autograd graph, and also there are receive and send pairs to pitch them together. And then when we call the backward pass using distributed autograd on the loss tensor on W0, it can also traverse the entire distributed autograd graph to compute gradients for X and Y respectively. And then we can call a step on distributed optimizer, which can apply the gradients to update X and Y using the given optimizer. So now let's go back to the original question. Why we need an autograd context? For this specific example, we don't need a context. We can store the gradients in x.grad and y.grad. However, for distributed training, especially distributed monoparallel training, there are cases where you can have, say, multiple parallel independent trainers talking to the same set of sharded parameters. And each trainer are operating independently, not talking to other trainers. And then in this case, they have their own independent forward and backward passes. And those forward and backward passes are all going through the same set of sharded parameter servers. And when that happens, if we don't have this dedicated context for each trainer, what can happen is that after the first trainer backward pass computes the gradients for a parameter of a sharded parameter server's say embedding table, and then there might be another trainer has already finished this optimizer step. It's gonna maybe just clear the gradients on the parameter server actually before the first trainer consumes its own gradients. And when that happens, basically we have a race, and the trainers won't be able to consume the correct gradients, or worse, maybe the gradients will just be none, and the trainer won't get anything. So to solve that problem, we actually have this autograd context idea, where all the gradients generated within this context actually have its dedicated place to store. So even if, say, they all share the same sharded parameter server, the sharded parameter server going to have multiple dedicated contexts, one for each trainer. And those contexts gonna store the gradients generated by that specific trainer. And so in that way, we won't run into the race problem anymore. And this is actually the solution that allows you to run the hot-wired training with sharded parameter servers. Yeah, we're at time. I still have some more slides, but I want to pause here to see if there's any question on distributed autograd.
So Shen, maybe what I would suggest is going through the rest of the presentation a bit rapidly so you get a chance to conclude and tell us a bit what you are
Sure. Yeah, thanks. Sure. Then let me move on. So the next thing I want to describe is why do we need RPC? Or when can we use RPC? We try to expose RPC as a low level and a flexible API, and to facilitate users to build their own training applications and training paradigms. We have tutorials to show you how to use RPC to build parameter servers, build general model parallel solutions, build pipeline parallel solutions. Those are all example cases, and there are also more advanced and complicated cases we solve internally using RPC. And then after that, I want to briefly talk about some of the hybrid parallel solutions. The first combination is to combine pipeline parallel with data parallel. Pipeline parallel is one way for model parallel training. In this case, we actually have the model sharded into 2 devices, and then we're going to partition every mini batch into multiple micro batches, and then run through those micro batches into those 2 model shards in parallel. And then when the local backward pass in every pipeline is done, we can kick off the communication for DDP reduce. And today's PyTorch already supports this combination. You can already use pipeline together with DDP. And Chaoyang has a fancy paper called Pipe Transformer, try to further accelerate that significantly based on the observation that we can freeze the models incrementally and spawn more pipeline replicas to increase the data parallel width. I'll skip the details of this. And another public structure we have seen so far is that people are trying to use RPC with the DDP in a way that whenever you have a large embedding tables, or whenever you have a sparse embedding tables, you might want to extract that embedding tables out from your model. Because if you have large embedding tables, it's very likely that the embedding table won't fit into GPU or even won't fit in the CPU memory of one machine. And whenever you have sparse tensors in your model, then DDP's collective communication will be slow. And why it's slow is because for the sparse tensors, the number of non-zero elements are not deterministic. It can change in every iteration. And the representation of sparse tensor in PyTorch is basically a combination of two dense tensors, one for the indices and one for the real values. And because we don't know what are the number of non-zero elements in other peers, so when we want to run collective communication on those sparse tensors, we will have to first run a altogether to get the number of non-zeros and use that to prepare the local buffer on each process, and then run another altogether to get the real value. In contrast, if we only have dense parameters, we only need one collective communication because the size of the tensor is known. It's just the size of the parameter itself. So in that case, as a result, DDP cannot support sparse tensors efficiently. Today, if you choose glue backend, it will work, but it will be kind of slow. So a recommended way would be extract out the sparse tensors and put that into parameter server and try to use RPC to communicate sparse tensors and use DDP to synchronize dense tensors.
Yeah, I have a question here. So I feel this is very useful for deep learning recommendation system, right?
Yeah, exactly. That's actually one of the use cases we saw internally.
You already use this for Facebook recommendation system? I
actually don't know whether I can share that, but I won't deny.
Okay. So yeah. Hi, K-Sharp, do you have any question here because you are working on this?
Well, so I don't have a question. The thing about the one thing that this would make me question is how frequently are we going to be invoking these RPC functions to move data between wherever the embedding tables sit and, let's say, the CPU and the GPU, right? Because you could potentially have two levels of communication if you want to move things from, let's say, like NVMe to the GPU, right?
Sorry, can you repeat the last sentence?
No, so I mean, but the basic question is how frequently would we be needing to invoke these RPC calls, essentially?
I see. So in general, we would recommend try to use the RPC calls as infrequent as possible. And that's something that the application needs to optimize because RPC calls are definitely more expensive than local.
Expensive, right?
Yeah.
Right, exactly. So I know that the recommendation model that is part of the MLPerf benchmark does not use, they actually have like an all reduced based, but then again, that system is reliant on just scaling everything out with if they don't have, if all the tables cannot fit on one GPU, just throw more GPUs at it. So I think that's the same model from Facebook, which is part of the benchmark, is just it's not using any of this right now.
Right, the open source DRM is not using any of the RPC right now.
Yeah.
I think I can comment on the general sense of the distributed training. So there are I think people are going towards two different directions. We see Google and Microsoft, they are trying to go through the single program multi-device training, where you actually don't need RPC to build a flexible structure because every process is going to run the same code and going to have a shard of the model. And there are also efforts, say, from Amazon trying to push the parameter server to the extreme, and they actually also show that parameter server can be faster than collective communication. So I think this is still an ongoing discussion.
Yeah. So we've been actually working on ways to like look at working sets of embedding tables and only use what we need. So there's certain observations that can be made because of the sparse nature of, and we don't need RPCs at all. Because like you said, you basically only want to, what the point of the RPC is, like you said, was to just take out what you need. If we can compute that in, let's just say, abundance beforehand and take them all out, that's essentially a way we'd be reducing this quote unquote, whether we use an RPC to take the data out of the embedding tables or any other mechanism. Yeah, go ahead.
Yeah. I mean, if there's ways to say avoid doing collective communications on sparse tensors in your model, then you probably don't need RPC. Yeah, I agree with that.
Right, exactly. And I think we actually exchanged some messages on the PyTorch forum about this. on how
Oh, I see.
and we basically concluded that sparse, like essentially any kind of collective communication using sparse gradients is inefficient.
Yep.
I mean, that's what we concluded. So we actually found of course, it depends on the use case, right? Recommendation models just so happen to be one case in which sparse gradients come up. But in this case, we have, like, it so happens we have a way to avoid making collective calls to sparse tensors, but I don't know if that's possible in any general case where you have sparse gradients. So yeah, I can see why this RPC would be useful in those cases.
I see. Yeah, I would be very interested to learn how do you avoid launching collectives on.
So I think we're actually writing a paper now, which we probably will submit to Rexis in May. So maybe I'll send you the link to the archive once we put it out.
Cool. Thank you very much. Yeah, I think this one is just a short survey on a summary on the existing hybrid parallel solutions. We can skip this one. And lastly, I just want to say thank you everyone for joining today's talk. And it's a great experience. I'm super excited to discuss with you on distributed training. And I learned a lot from this discussion. Thank you.
Thank you, Shen.
Wonderful. Thanks so much, Shen. I mean, there were a lot of questions, but maybe if there are follow-up questions, we can spend a couple of minutes here. Otherwise, we wrap up the talk. All right. I think
I don't have any. I don't have any questions. But then, I guess I'll just send you like I'll post on the PyTorch forums if I have any questions.
Cool. Yeah, that's a great place to go. Thank you.
Very good. So Shen, Choyang and I were planning to have some discussions with you. So maybe what we can do is, we can create another Zoom call and we join there.
Sure, that sounds great. Thank you.
Good. All right. Thanks, everybody.
Thank you, Shen.
Thank you.
Thank you, everyone. Shen. Bye.
Thank you, Ryan. Thank you, Shen.
Thank you.